In this video, you will see a basic overview of heat transfer modeling in Fluent. To include heat transfer in your Fluent simulation, all you have to do is turn on Energy in the Models section of the Setting Up Physics tab. There are three modes of heat transfer: conduction, convection, and radiation.
Once Energy is on, with an Enterprise or Premium license, Fluent can solve problems involving any and all of the three modes. And with a Pro license, it can solve problems involving conduction and convection.
If any solid zones are present in the model, Fluent will solve for conduction in the solid. The picture shows an example of conduction where the lower surface of the pot is being heated by the stove and the sidewalls get warmer by conduction through the metal. If any fluid zones are present in the model, Fluent will solve for both conduction and convection in the fluid. It's possible to have solid zones and fluid zones in the same model. In such a case, the solid and fluid are thermally coupled at the solid surfaces, and Fluent handles this automatically. In convection, fluid flow transports heat to or from a surface, so in the diagram, which shows a warm object immersed in a stream of cooler fluid, the object warms the fluid that comes into contact with it. The flow transports the warmer fluid away from the object, replacing it with cooler fluid, which allows heat to be removed more effectively than what would be possible by conduction alone. In convection, the flow can be driven by external means, which is known as forced convection, or it can also be driven by buoyancy forces that result from density changes caused by the heating or cooling of a fluid.
This is called natural convection. If radiation is important in your problem, you can click on Radiation and enable one of the radiation models. And additional details on radiation modeling will be discussed later.
When you set up a heat transfer problem, you have to define thermal boundary conditions and thermal material properties.
Thermal boundary conditions is a big topic that we will discuss later, so right now I will just talk about material properties.
For heat transfer problems, you need to define values for thermal conductivity and for specific heat. Thermal conductivity is a key component of any conduction problem. In conduction, the heat flux is governed by Fourier's law, which says that the heat flux vector is proportional to the temperature gradient, and the conductivity K, which you see here, is a constant of proportionality in Fourier's law. Thermal conductivity can be defined as a constant value or as a function of temperature. In most regular materials, it is a scalar, which means it has the same value no matter what direction heat travels. But in anisotropic materials, thermal conductivity is a matrix, and it can have different values in different directions. Fluent has numerous anisotropic models, so that for instance you can simulate composite materials. Specific heat is important because it helps determine the temperature change that results from heating or cooling something by a certain amount of energy. For example, if you add a given amount of energy Q to a mass m of a material, which could be a gas or a liquid or a solid, the temperature in that mass will change according to the amount of energy and the specific heat. As with thermal conductivity, for some problems it can be important to define the specific heat as a function of temperature. It's recommended to use double precision when you solve heat transfer problems. Remember that you can tell Fluent to use double precision in a launcher panel. The reason that double precision is recommended for heat transfer problems is that in most cases, it makes it easier to get a good energy balance. To check energy balances in a heat transfer problem, you'll use the Flux Reports panel. In the Flux Reports panel, you can see that there are options to either report the total heat transfer rate or to report only the radiation heat transfer rate if your problem has radiation. The total heat transfer rate includes both convection and radiation. Because of this, the net value should be 0 for a converged solution. There's been a lot of material covered in this video,
so before moving on, let's just briefly review what has been covered so far.
Fluent can solve problems involving all modes of heat transfer: conduction, convection, and radiation, and it can model processes such as conjugate heat transfer and natural convection. When you solve a heat transfer problem in Fluent, start Fluent in double precision, activate energy, and if you're including radiation, activate a radiation model. Define thermal boundary conditions and set the values of thermal conductivity and specific heat. And finally, when your iterations have finished,
go to Fluxes in the Results tab.
And check the energy balance to make sure that the solution is converged.